Apples were a very bad snack to pick for this occasion. Sorry if my chewing sounds are loud. Yeah. Okay, so I'm going to continue talking about emergence, particularly in the context of this paper. And I'll read the abstract again. There has been much controversy over weak and strong emergence in physics and biology. As pointed out by Phil Anderson in many papers, the existence of broken symmetries is the key to emergence of properties in much of solid-state physics. By carefully distinguishing between different types of symmetry breaking and tracing the relation between broken symmetries at micro and macro scales, I demonstrate that the emergence of the properties of semiconductors is a case of strong emergence. This is due to the existence of quasi-particles known as photons, such as phonons. Furthermore, time-dependent potentials enable downward causation, as in the case of digital computers. Additionally, I showed that the processes of evolutionary emergence of living systems is also a case of strong emergence, as is the emergence of properties of life out of the underlying physics. A useful result emerges. Standard physics theories and the emergent theories arising out of them are all effective theories that are equally valid. Okay. I'll do my best to not chew into the mic. Okay. So we can say that a high-level phenomenon is strongly emergent with respect to a low-level domain when the high-level phenomenon arises from the low-level domain, but truths concerning that phenomenon are not deducible, even in principle, from the low-level domain. So we have two aspects here. The fact that a high-level phenomenon is arising from a low-level domain, but also the fact that truths concerning this phenomenon and the principles governing this phenomenon are not deducible from the low-level domain. So if that sounds familiar, it's because it's similar to... actually, it's directly related to undecidability. So undecidability is this phenomenon in mathematics where if you have a complete mathematical system of basic axioms which you can use to do arithmetic, so it's a powerful system, not just like an arbitrary set of axioms. There's going to be true statements within that system, inevitably, that cannot be proved using the components of that system. So it's like this new truth. And if you assume, if that truth is valid for a given situation, it means that more truths are deducible from that. But that process of introducing that principle within your mathematical system is actually going to introduce new statements that are also unprovable given that expanded system. Okay, so it's just a consequence of the way we systematize and axiomatize math. And it's a relatively new result, new as in like I think in the 1930s. And so that's why, to the extent that this principle has been discovered, it hasn't been applied to the idea of free will so much. And so free will so far, because this principle hasn't been explored within the context of free will, the arguments against free will have so far succeeded in convincing a lot of people because they are convincing given their own axioms. It's just that there are aspects of reality that those axioms don't fully cover. Anyways, let's continue. In strong emergence, properties are only deducible from lower level properties when you add concepts or variables that are derived from our knowledge of the nature of the higher level emergent domain. The lower level simply does not by itself imply the relevant higher level concepts or variables. One needs empirical input from the higher level theory to determine such bridge laws. there's lots of examples of this as well. For example, um, there are some phenomenon in physics that that if you tried to calculate or tried to predict using the standard laws of physics, you're going to get the wrong answer. And so you have to add this additional component, and then you'll get the right answer. But the question is, where did that additional component come from? Well, first of all, the additional component emerged as a consequence of those laws within that system of laws, but as a truth which is unprovable in terms of those laws. So it's within that system, but you can't use the system to derive it. And then once it starts to exist in nature, humans can observe that system or that concept and then add it, and this will help us explain the phenomenon and capture the mathematics surrounding it. This is really important to know and to remember. You have to add concepts. Properties are only deducible from lower level properties when you add concepts or variables that are derived from our knowledge of the nature of the higher level emergent domain. So we can bridge the gap between our lack of understanding, our lack of ability to demonstrate that a truth exists within a particular axiomatic system, by observing that truth in nature and then re-adding it to the system. Okay, so for example, I'll refer to this example a lot because it's a good one. If you take Euclid's elements, Euclid's like 5 fundamental axioms for geometry and math and arithmetic, the first 4 are pretty logical and seem to make sense. The 5th one was shown to be unprovable within that system. It's just something that's true or not. And it exists in the real world. So when that system is true in the real world... someone's at the door. Let me just close the door. Teddy! Stop it! Apologies if you hear my dog barking a bunch. He's going to be barking until he can greet the person. Okay. Lower level simply does not by itself imply the relevant higher level concepts or variables. One needs empirical input from the higher level theory to determine such bridge laws. This in and of itself is not implying undecidability, but you can see an undecidability is baked into this. Because, like, where would those concepts even come from? And also the fact that those higher level concepts are not implied by the lower level concepts should imply that the lower level concepts are incomplete for describing all truths concerning that system. Even in principle. So this is a really crucial point to keep in mind. This is probably, so I said before, earlier today, that this is my favorite paper that I've looked at so far, even though a bunch of them are really good. But I think that this is like the strongest case for strong emergence, as observed both in reality and as confirmed by the mathematics. It's wonderful. It's wonderful that this was written by George Ellis. Can I even open the paper here? Yeah, so this is, just so you see who the author is, and when he wrote it, 2020. Fairly recent. Probably why it hasn't received so much widespread notoriety. Okay, let's continue. So strong emergence, you need new concepts at the higher level, but is this limited understanding or difficulty using lower concepts? No, you really do need new concepts. So I made this note for myself, reading the paper, probably just summarizing what he said, where he might have asked a question like, so is it because of our limited understanding of, or our limited computational abilities at the lower level that's causing us to be unable to understand this higher level concept?
Um, the principle there is rather straightforward. Is that, like, imagine you tried to use the fundamental laws to predict something, some higher level emergent phenomenon, but your computer just isn't strong enough to run the computation, and so you keep getting the wrong results. And so maybe it's just a matter of the fact that we need more powerful computers to be able to run these simulations, and then once we have that computational power, we can derive the higher level laws no problem. This isn't actually the case. What George is claiming in this paper is that you really do need new concepts because there's like a fundamental breaking that occurs between the lower level and the higher level domains, where the lower level laws just no longer apply to these higher level domains. And we'll see how that manifests much more clearly. Okay, so solid state physics is the physics of semiconductors. Crystallization is a case of weak emergence, which arises due to energy minimization as the crystal forms. Um, yeah, so this is just referring to a case of weak emergence where a particular crystalline structure emerges out of the way molecules are arranged, and there's nothing really surprising about it. Um, they are not naturally occurring, but are the outcome of purposeful design. And so he's referring to the crystals that are used for semiconductors. Um, Once they exist, their properties might be strongly emergent, and the reason is because of broken symmetries. Now, the idea of broken symmetries is something that is discussed in this paper, and I think I understood it when I read it, but as I'm thinking about it now, it's not really coming to mind. I've been familiar with the concept of symmetries from physics for a while, but I didn't really understand their significance because in physics you hear all the time about supersymmetry being like really important, and you have like Noether's theorem, which describes the symmetries of nature, and there's things like symmetry breaking, um, that the Higgs mechanism that gives everything mass involves symmetry breaking, and there's also like symmetry breaking that you can think of more generally, which is in the phases of matter, the states of matter. So, for example, like water is a liquid within a very specific range of temperatures, but then you go to negative temperatures, so 0 degrees Celsius and lower, and then the water freezes. So, like, there's this sudden shift where where the behavior of the material changes and the symmetry breaks as a result of decreasing temperature. And so that would be an example of symmetry breaking. I think that's even brought up here. Give me 1 second to just take a bite of my apple and contemplate what I just said. Apparently, I have 0 viewers. Okay. The emergent lattice structure in semiconductors leads to the existence of quasi-particles that inextricably link the lattice and electron levels via a quantum physics effect of interlevel wave particle duality. Don't understand what that means, but I thought it was significant enough to write down. The emergent lattice structure in semiconductors leads to the existence of quasi-particles. I guess that is itself significant. And the quasi particles in this situation are the kind of new thing that has emerged. Like quasi particles don't exist in and of themselves; they exist within particular contexts, um, in specifically particular crystals. And so the crystal structure gives rise to this new thing called quasi particles that now have an impact on the lower level domain, upon the particles of which the crystal itself is composed. This paper says that there are other excellent examples of strong emergence that he doesn't talk about, like fractional quantum Hall effect. So, I mean, I don't know exactly what this is, but the fact that I'm assuming is something that occurs at a very small scale. So it's evidence of a strongly emergent property emerging at a very low level of physics.
topological insulators, I might look into that, and cases in soft matter physics. In the case of biology, the coming into being over long periods of time of species is a case of strong emergence because of the contextual nature of the selection process. So again, another paper that's showing that evolution is a strongly emergent property. Okay. So he goes on to say, firstly, I will claim strong emergence is the result of a combination of upward and downward causal effects. It is the downward influences that enable higher levels to shape lower level dynamic outcomes in accord with higher level emergent dynamics and needs. That's worth repeating. Firstly, I will claim strong emergence is the result of a combination of upward and downward causal effects. Okay, so a combination of upward and downwards. It's not just the upwards. It's not just the downward causal effects that characterizes strong emergence, but something about both of these that causes strong emergence. I mean, that makes sense. It's so complicated though, and it's even like hard to understand the timing of it because like when does the strong emergent principle happen? When the higher principle or higher level domain has influence on the lower level, or is it just before that? So it's a combination of both upward and downward causal effects. It is the downward influences that enable higher levels to shape lower level dynamic outcomes in accord with, it is the downward influences that enable higher levels to shape lower level dynamic outcomes. So the higher level has this influence, this downward causal influence on the lower levels in accord with higher level emergent dynamics and needs. Yeah, it would be super nice to just get an example of this. And also, like, I guess all of this would have to incorporate compatibilism. Compatibilism as a way to rescue free will, because you add to your chain of causation the idea of the self. And if the idea of the self has causal efficacy, you must have free will. And so it's just a matter of showing that the self or the psyche has causal efficacy, independent of its own causally generated circumstances as a result of matter. Because matter is necessary for the existence of a psyche, at least in our universe, and at least according to what we've observed about the universe. But then once the psyche comes into existence, the psyche can have this downward influence on matter, and it can also act apart from matter. Okay, where was I? It seems to be assumed by most physicists that this is indeed the case. I guess this is the case that you don't need higher level dynamics. There is an underlying, most basic level, a theory of everything, or TOE, T-O-E, from which all else follows. However, the problem is that we do not have such a well-defined and tested fundamental theory to which all else could in principle be reduced. We do not even have a proof that such a level exists. That is a supposition. That supposition is an unproven philosophical assumption which may or may not be true. This is super key because the entire case for causal determinism is grounded upon there being like the most fundamental theory that all matter is pretty much just conforming to. The standard model Lagrangian
is probably the best example because it's just the laws of motion and the laws of interaction for the fundamental constituents of matter, which are fundamental particles. But there might be a deeper theory. But we haven't discovered a deeper theory. The standard model theory is the best that we have. And so we don't. So first of all, we don't have a theory of everything. We're still working on it. Second of all, it raises the question of whether you can even use the standard model Lagrangian to argue for determinism if it itself is not a fundamental theory. It itself might be an emergent theory from more deeper fundamental truths. And so if you use the standard model Lagrangian to show that causal determinism is just the way that the universe works, and that there's no such thing as strong emergence, you're kind of on shaky ground there, no? Because you're operating with a theory that you don't even know is the most fundamental theory. That's just a claim, and that's just a belief. There could be more fundamental theories, or this theory itself might not really apply with equal validity to all domains, which is what I'm arguing, which is what this paper is arguing. Okay, still have 0 viewers. I appreciate it. Appreciate the nobody's watching. So we have no proof that such a level exists, and this is a supposition that's right now unproven. No such theory currently exists. It's just assumed to exist. I can't wait to bring that up in an argument. In this paper, section 6.4, I extend that statement to a generally applicable principle of equal causal validity. All emergent levels, whether physical or biological, are of equal causal validity in that they support an effective causal theory that may be considered to be valid at that level and is not trumped by effective laws at any other level. What's going on here is probably very important to understand for people who want to use the theory of emergence to derive further principles and understand deeper levels of reality. But I'm not sure how valid it is for free will because, okay, let's just say free will exists at a particular plane of existence. At the level of the psyche and at the level of psychic existence, which is a very higher level domain compared to physics, free will exists. Okay. What this is basically saying is that there could be a set of rules and principles which explain how free will operates, which is itself a valid theory. Like it's not a less fundamental theory than the theory of matter. In fact, it can't be a less fundamental theory. It's a theory that applies at the specific level of reality, and the theory of matter actually doesn't apply. So matter is itself invalidated, and it's this higher level principle, this higher level effective theory, which is actually relevant and applicable to this higher level domain. Okay, let me just take a bite, and then we'll continue. Okay. This was a very long paper, by the way. Let me just quickly check how long it was. If it even says. It was 41 pages. That's a lot of reading to do for an academic paper like this. Okay. I see that I have 2 viewers now. For a while I was just talking to myself, but hello to my 2 viewers. Hope you're doing well. And hope you don't mind listening to me ramble on about the things that I've been researching and making notes of. I'll just say what I'm doing again. This is a paper that I read recently, and I take a bunch of notes on it, and now I'm just going through my notes to consolidate what I've learned. Okay, so an effective theory, ET, is a theory which effectively captures what is physically relevant in a given domain. So like each domain has its own set of rules which are applicable to that domain, and you don't have to consider lower level domains to derive principles
or to understand that domain. So like economics is like a higher level domain that doesn't exist in matter. It exists in human societies, but there are rules of economics that you can apply to economic systems to predict things, and understand economics, and treat it as though it were its own science. You don't need to refer to particles and particle science in order to do economics. You can just use the principles of economics to understand economics. And in fact, you might think to yourself that it's like if we could derive economics from particles, that would be ideal because that would be more accurate. Well, actually, this paper is saying no, it wouldn't be more accurate. It would be wrong. You can't in principle use those lower level ideas to get higher level to get functionality and to get accurate predictions in higher level domains. You can't. So you would actually be wrong. You need those higher level concepts in order to operate. Where theory is a set of fundamental equations or simply some Lagrangian. I guess that doesn't apply so much for economics, but there are like economic differential equations that I've seen for describing some entities, their behavior, and interactions. More precisely, an effective theory is an appropriate description of the most important relevant physics in a given region of the parameter space of the physical world. It is therefore an intrinsically approximate and context-dependent description. Again, that just reiterates what I've been saying, that like the rules that apply in a particular domain are specific to that domain and are completely valid within that domain. And in fact, like even though our intuition might tell us that, so for example, like we want to do biology and we want to know what a cell is going to do. So we have some rules for biology that cells they try to survive. So that's one principle that we can apply to understand how a cell operates. But then you might have this intuition where like, well, actually, if you knew the positions and momenta of every particle that composes the cell, that would be a much more accurate model for what the cell is going to do. Whereas the other theory, the theory that operates at the level of biology, is kind of provisional or less accurate or a simplification, and that would actually be incorrect. If you attempted to understand a cell and the way it moves purely by referring to the matter, you will be wrong. It's because there are truths which apply to a cell that don't apply to the fundamental constituents of that cell. The whole cell has a new kind of like domain where the rules that govern its parts don't apply to the whole cell, which is very fascinating and again well established and well proven in this paper. I'm snacking at the same time, by the way, if you guys don't mind. It'll help me say what I need to say as I discuss this. And if either of my two viewers have any questions or comments, even if you have no idea what the hell is going on because you just randomly found this stream and you just have no idea what this could even be about, feel free to ask and I'll try to clarify what's going on. Okay. It is therefore an intrinsically approximate and context-dependent description. A key thing about this is that all emergent levels are equally causally effective because every level L has an effective theory with it, ETL. So an effective theory level and an effective theory. There is no privileged level of causality. Two aspects of emergence are emergence of systems and emergence of properties. So he makes this. He gives these descriptions for very important aspects of emergence, and I'll read them now. Emergence E of system from its components. So this is just referring to like the structure, a new kind of structure from components. For example, the emergence E of nuclei out of protons and neutrons. Yeah, so that's a good example. Just the fact that a nucleus can emerge from constituent elements, being protons and neutrons, of water or a metal or hemoglobin molecules out of the underlying nuclei and electrons, or of a human body out of its constituent cells. Okay, so it's purely structural. This is purely a structural description, like higher structures emerging from lower structures. The issue of phase transitions is important here. These occur when a major change in the emergent state takes place, such as the transition of water from a liquid to a gaseous state when boiling occurs. This is interesting. The phase transition. I know that these are very relevant for emergence, the fact that there are phase transitions. And I'm also interested in dynamical systems theory and the mathematical descriptions of dynamical systems. And I know that that's somehow relevant here, but oh man, it's going to be hard to merge dynamical systems theory with emergence. But just know that emergent systems in general are dynamical. So then he also talks about emergence P of properties. So this is different from just the structural changes that can occur when you build something out of smaller constituents. What this refers to are the fact that those new structures can have brand new properties, like brand new capabilities. Not just a different kind of rearrangement of parts, but by rearranging these parts in a very specific way, you get this new property. So, for example, if I arrange components in the shape of a computer, that computer now has this property of being able to compute, to being able to do things that a computer does. And so the arrangement can give it new properties. Emergence P of properties, properties of the emergent system out of its underlying constituents once it has come into existence. How do such properties of a nucleus arise out of the nature of its constituent neutrons and protons, and theirs out of the constituent quarks? How do rigidity or electrical conductivity, so these are examples of higher level properties, or optical properties of a crystal, or chemical properties of a molecule arise out of the underlying electrons, protons, and neutrons? How do properties of a cell in the human body arise out of properties of its underlying biomolecules? How does behavior arise out of those cells? These are all the questions that we need to contemplate. And at this point, either things like that arise weakly or they arise strongly. But this paper goes into the evidence of strong emergence. Okay, and then he brings up the concept of symmetry breaking. Actually, I'm just going to take a quick bite while I have this minute. Oh, just got a text. Okay, so he brings up the concept of symmetry breaking. So this is something that I need to study because I made notes on it. Hopefully I've explained it thoroughly enough that I can understand it. So there's symmetry breaking, spontaneous symmetry breaking that occurs at the micro level, indicated by small m. Spontaneous symmetry breaking that occurs at the macro level, indicated by big M, due to process E, so emergence, creating that level from micro level M. So emergence creates a new macro level out of a micro level. Okay, that's simple enough. And then he talks about symmetry breaking NS is symmetry breaking in biology that has occurred due to Darwinian processes of natural selection, leading to the existence of specific kinds of molecules at the macro level M. Not sure how relevant that will be. I should turn off my night light. Oh, no. Okay, when that turns on, I'll turn it off. Okay, broken symmetries are key to emergence in condensed matter physics. Crystalline states are broken symmetries.
Okay, so this will get into an example of a broken symmetry and help clarify it. Why do we call the beautifully symmetric crystalline state a broken symmetry? Because symmetrical as it is, so like a semiconductor crystal, the crystal has less symmetry than the atoms of the fluid from which it crystallized. These are in the ideal case featureless balls, while the crystal has no continuous symmetry or translation symmetry. Oh, okay, what the hell is happening here? Because symmetrical as it is, the crystal has less symmetry than the atoms of fluid from which it is crystallized. Okay, interesting. It has less symmetry. These are, in the ideal case, featureless balls, while the crystal has no continuous symmetry or translation symmetry. Okay, so like even though it's symmetrical, it's like somehow less symmetrical than the parts. Thus, the symmetry of a crystal breaks the translational invariance of the theory that underlies it and leads to the Bloch wave functions that are key to much of solid state physics. Okay, so this is probably some theory that now applies to solid state physics, which doesn't apply, which is useful for solid state physics, but maybe that this theory, Bloch wave functions, is an emergent theory from this crystal structure. Thus, the symmetry of the crystal breaks the translational invariance of the theory that underlies it. It breaks the translational invariance. Okay, so there's a symmetry here, translational invariance, that's supposed to apply to the lower level theory, but that theory is broken because of the crystal structure. Okay, so we can. This is fairly straightforward then, because we can identify whatever symmetries are supposed to exist in a theoretical model. For example, in standard physics, the principle of conservation of energy is a kind of symmetry. At least I think it is. Someone correct me if I'm wrong. My one viewer, correct me if I'm wrong. if energy conservation is a form of symmetry, but it's a form of symmetry because energy is always conserved. But you can break that principle in certain contexts, and then the symmetry is broken, so that energy is not conserved. And so it seems like in this case, translational invariance is a symmetry that's being broken, which is leading to the Bloch wave functions that are key to much of solid state physics. By Bloch's theorem, the electron wave functions in a crystal. Need to get a better setup. In a crystal has a basis of Bloch wave energy eigenstate. This feature underlies the nature of electronic band structures and thus, for example, determines electric resistivity and optical absorption, which are measurable phenomena. This feature underlies the nature of electronic band structures, and thus, for example, determines electric resistivity and optical absorption, which are measurable phenomena. Okay, so I guess that Bloch's theorem is a kind of new way to describe the energy states or electron states of this crystal structure, and then these additional phenomena, resistivity and optical absorption, are like these new emergent phenomena that occur out of this situation, that occur out of the fact that the symmetry up here has been broken, that the translational invariance of the theory has been broken. Okay, so that's interesting. What this means is that the physical properties of the emergent state, the specific crystal structure, reach down to influence the motions of electrons moving in the lattice. So very cool. What this means is that the physical properties of the emergent state, so the crystal itself is an emergent physical structure from molecules, but this physical state, this brand new thing that has occurred as a result of molecules, now can have this downward influence on the motion of electrons through the lattice. The structure itself is influencing the particles. Like the smaller particles that are supposed to be the thing that make it up, it's having an influence on those particles. So it's not just being caused by the particles at the lower level, it's also having this causal influence on the particles. Excuse me while I take a bite from my snack. I've noticed every time I do that, I lose viewers. But that's fine. That's a downward effect underlying the key physical properties of semiconductors. So it seems like the physical properties of semiconductors rely on the fact that this higher thing can have a downward causal influence on the on its constituent parts. And this really underscores what I was saying earlier, that like if you try to use the basic laws of physics to derive some of these principles, you're going to get the wrong answer. And these systems are pretty simple. So computationally, you should be able to show that they're weakly emergent. But you can't show that because you'll get the wrong answers, because there's this interesting dynamic occurring once higher level properties start to exist. That's having an influence on the matter, on the fundamental constituents, and that influence is going to is not really being accounted for when you do your physics, because when you do your physics, you're just assuming that it's these particles interacting with these laws, and you're not considering these higher level laws and the effect that those higher level laws can have upon those constituents. He gives Ohm's law as a specific example. That's incredible, by the way. Ohm's law is like very well known, and like if you've studied like any basic electricity, you know about Ohm's law. And there's no way to derive Ohm's law from fundamental principles, which he says here. Consider as elementary a principle as Ohm's law, like very elementary. As far as I know, no one has ever come even remotely within reach of deriving Ohm's law from microscopic principles without a whole host of auxiliary assumptions, physical approximations. I was thinking of pausing here for a second. I mean, I'll just read the whole thing because it's quite a fascinating realization when you realize that something like Ohm's law itself is not derivable from microscopic principles, which one almost certainly would not have thought of making unless one knew in advance the result one wanted to get, and some of which may be regarded as essentially begging the question. Okay, so there's some key things to highlight here. You can't derive Ohm's law from microscopic principles alone. You need to add some auxiliary assumptions, okay? So these auxiliary assumptions are like these brand new truths that have emerged within a specific context. And so these brand new truths are having an influence, a downward influence on the fundamental constituents, such that this new principle is emerging, in this case Ohm's law. And so if you don't account for these higher level principles acting on the lower level domain, you'll get the wrong answer using the fundamental principles alone. You need to include some emergent principles within your model in order to get the right results. Again, this relates much to incompleteness, because you can think of these host auxiliary assumptions as being truths within the system of physical assumptions of microscopic principles that are not derivable from these microscopic principles. They're like additional truths that just happen to be true, but not provably true within the microscopic principles. So you need to add them as additional considerations within your physical model, and then you'll get the right example. So that's what these auxiliary assumptions refer to. These additional physical approximations that you need to incorporate into your model to get the right result, which you can't figure out from the principles of the model itself.
You can only figure it out, I guess in this case, from observing Ohm's law, and then you can add those physical approximations. But think about this. What you're actually doing is you're waiting for the emergent phenomenon to exist, and then you're jumping in and being like, okay, so we can see it now, and we know what principles are needed to get it to work. We're gonna add those principles in an after the fact manner and get the right results. But the only reason we could do that is because the emergent phenomenon exists in nature for us to observe and then for us to add to the model. We can't get the emergent phenomenon from the in his words, from the microscopic principles. It's just not possible. And this is a very eerie fact about the universe, but one that's completely consistent with mathematics, although it's a fairly recent discovery in mathematics. And it's a discovery in mathematics which led to the invention of the device that you're watching this on right now. Assuming you're watching this on a phone or a computer. Okay, so yeah, this is a very, like, God, how did I not go through my life without knowing about this? I mean, it came about recently. I got a comment. Just jumped on, but I'm hyped to catch this live. Better late than never. Yeah, I agree. If you have any questions, sir, feel free to ask, because this is some complicated stuff, and more questions people ask, the better. Been a huge fan of these videos for a year or so. Oh, thank you so much. Thanks for watching. And it's nice to have you commenting here. I definitely want to get back into like making my normal videos of like just Jung and the bicameral mind. And I do want to get back to my basics, because I'm going to start using Jungian psychology more as I become a psychotherapist. So I need to kind of get back to my fundamentals. But in the meantime, while I have some downtime, I'm going to be studying these super high level physical concepts that are some of the most enlightening ideas I've ever come across. Like, this has just opened my mind to like so many possibilities. And I feel like I can now grasp why the universe is such a strange place. Now I get it. Like, this has opened the door for me to understanding why think about things like language and how weird language is. Like the fact that like I'm making sounds right now and that you're understanding them. Well, in the context of emergence, you can see how it's possible that something like language can exist. But pure reductionism can't actually get you to language. And so this is very contrary to reductionism. That's what I'm basically doing. I'm just showing the theory that's utterly at variance with reductionism. Okay, I'm going to take a quick bite of my apple. Sorry for the chewing sounds if they're loud. But it's kind of like ASMR, no? Okay, let's continue, because I really hope to get through this paper by the end of the night, and I'm definitely not on schedule. Let's see, hold on. So this is how much I've gotten through, about up to here, here, and from here downwards is what I have to do. Oh boy, am I gonna be able to do this? Jesus, what am I even doing? And also, why am I even doing it? Okay. So to summarize what, this will summarize. Thus, one often needs some additional and distinct assumptions in order to derive an effective theory. These assumptions are usually called auxiliary assumptions and do not necessarily involve approximations. That's also key to important. Let me just, hold on. I gotta turn off my nightlight. That's also key to realize, is that these aren't always going to be, approximations in the sense of like you measured the phenomenon in real life and now you know what approximations you need in order to get it to work in theory. It could also just be kind of like an axiom you throw in. At least that's what I think, because I remember reading this and getting the sense that that's what he meant. Excuse me. Okay. This is what happens when we try to derive. This is what happens when we try to derive an effective theory in the bottom-up fashion, but need some extra information about the low energy degrees of freedom. Example, some new symmetry principle, in order to do so. Um, Again, this just speaks to the fact that you can't do this bottom up. You can. What happens is you start from the bottom up, you go up, and then suddenly you get something like a crystal, and the crystal is this new structure that has this influence on the lower level laws. So now those lower level laws aren't going to get you to the right answer, because there's this additional thing, this additional auxiliary assumption that's kind of interfering with the way the crystal is supposed to behave in according solely to those fundamental principles. Oh, I see some more comments. Love the Jungian bicameral stuff. But I happened to stumble upon Justin Riddle's channel talking about quantum consciousness and free will right as you started getting on the free will tangent. Perfect timing. I mean, maybe the timing isn't a coincidence. Yeah, so perfect timing as far as I'm concerned. Yeah, maybe it isn't a coincidence. Maybe that in a synchronistic way, people who think about this sort of stuff are converging on the same truths as the information becomes more readily available. Because so this whole thing about free will, like in my opinion, like it's been very obvious, but to be completely honest, it's actually a very hard thing to prove apart from materialism. So intuitively, we sense that we have free will. And I always say trust your intuitions over your deductions, your logical deductions, because your logical deductions are usually based on faulty axioms anyways. But if we assume that those axioms are true, it's actually very hard to argue for free will. But now scientists and philosophers and researchers from all kind of domains, from particularly computer science and artificial intelligence research, but even mathematicians are starting to understand these truths and these principles, which make it possible for the existence of free will, for free will to actually exist. And so we didn't know about these principles for a long time. And so I have to concede to people like Sam Harris a little bit that, like, as far as we knew back then, his theory about free will would be right. But now that we have the information that we have, I can show that his theory about free will is actually wrong. But I shouldn't be gloating about it because this is only recently discovered. And in fact, it's only been recently discovered by me. That's why I'm streaming about it right now and discussing it, because I'm really trying to understand it in order to make a video, which I'm hoping to write tomorrow, but we'll see how things go. Excuse me while I blow my nose. Okay. Can one derive the results in a purely bottom-up way? No. One can derive the micro-macro relation in an upward way, provided one inserts some of the macro picture either into the effective Lagrangian as a symmetry-breaking term, or into the micro-macro relation, as Weinberg does in his effective field derivation of superconductivity. See, these are all brilliant scientists who found ways to develop a theoretical picture of these phenomena, but notice how in either situation they had to insert some of the macro picture. So you needed to insert some of the higher level principles into the picture in order to get it to work, which already raises questions about determinism, because if determinism is all you need, why would you need higher level principles? You should be able to derive those higher level principles. Why do you need to insert them? That makes no sense until you know about emergence. And so there's very smart scientists who've been able to do this, but again, it's begging the question of why do they need to insert higher level physics? So instead of counting power, so I think he's describing how Weinberg did his effective field derivation of superconductivity. Instead of counting powers of small momenta, one must count powers of the departures of momenta from the Fermi surface. Without that ingredient, the derivation fails. So this explains just like the nature of what you need to add in order into your physical model in order for the derivation to work. But again, why do you have to add that in? The point then is that you can only derive the Fermi surface position from the macro theory. Thus, it is not a purely bottom-up derivation. And I think like this is kind of like a
an uninvestigated clue, because scientists, when they do this, like they're making these assumptions and then they're getting the right results, but then they're not asking the question like, why did I need to make that assumption? They're just like kind of mesmerized by the fact that they got the right result. And correct me if I'm wrong, if any of you 5 viewers know about fundamental physics. But my understanding is that the fundamental laws of physics themselves also require a bunch of fine tuning. So, for example, the mass of an electron, I don't know how to derive that. I mean, maybe you can derive it from the Higgs mechanism, but I'm pretty sure like some of the masses of the fundamental particles, you need to measure their masses and then add them into your picture. We don't actually know how to derive those masses from the laws of physics, which is like surprising, like because we have a fundamental theory. We should expect that fundamental theory to explain, for example, why an up quark has the mass that it does, why a neutrino has the mass that it does. But no, it seems that we have to measure these things and then add them to the model. So what's going on there? Allow me to, well, as you ponder that question, allow me to quickly take a bite. That's so funny. The second I mentioned that I'm taking a bite of my snack, I just lost half my viewers. They're like, nope. I will not listen to you chew. That's understandable. But I hope they come back. The point is that you can only derive the Fermi surface from the... Oh, got a comment. 1 second. Awesome stream. Tangent. Frank Herbert's The Santaroga Barrier is very relevant to this topic. The Santaroga Barrier? Never even heard of that. Is that a novel? And if it is, please let me know what it is and how it's relevant to it. I would believe that though, man. Frank Herbert's a genius, and like even in Dune, you can just see him like pondering ideas and topics that were only like explicitly talked about much later on. Like I'm pretty sure like you can see so much in there of like, for example, like the distinction between the right hemisphere and the left hemisphere and their modes of operation. Like, and this was before we had like a solid science establishing that the right and left hemisphere were actually different from each other. So he sensed intuitively what science would later discover explicitly. So I'm not at all surprised that he's touched upon this topic. It's a fictional novel by the same guy who wrote Dune. Yeah, I'll look into it, and maybe I'll give it a read as well. Because I've only read Dune by Frank Herbert. I wasn't even aware that he made other novels. But yeah, you can feel free to tell me about it. Where was I? The point is that you can only derive the Fermi surface position from the macro theory. Thus, it is not a purely bottom-up derivation. If you try one, you will fail. You will fail. This is what I was saying earlier. Like if you try to derive human consciousness from matter, you will fail. You will fail. It's not a matter of computational efficiency or power. It's a matter of the fact that the fundamental axioms just don't apply at that level. And so just using those axioms alone will not give you the right answer. It's essentially the book which carries the idea of the spice to its natural conclusion. Oh, interesting. Very interesting. I'm curious to see what that would be about. Cool. Okay, I definitely check that out. Okay. Computing power is not the problem. See, I even wrote this in my... Oh no, maybe he wrote this. Computing power is not the problem. You need the right concepts at hand. Yeah, I'll give you an example of this. So my 3 viewers, I'll give you an example of exactly what this is about. So you guys might be familiar with a theory known as quantum mechanics. And you might also be familiar with a theory called general relativity. So general relativity explains how gravity works, and quantum mechanics explains how particles work.
some of the assumptions um, that underlie quantum mechanics do not work and are completely incompatible with some of the assumptions of general relativity. So the theories actually don't work together. Um, and again, the problem isn't about computational efficiency. It's not about like you just need the right amount of computing power and then you can figure out how gravity works in quantum mechanics. They're just incompatible with each other. They involve a different set of rules. Um, Quantum mechanics involves the rule that space-time is flat. General relativity involves the rule that space-time is curved. So you have these different rules on different on different domains, um, and we have to know which rules apply to which domain. And it's very dumb and kind of arrogant to assume that the lowest domain of physics somehow applies to, for example, to human behavior, to love, to emotions, to qualia, to consciousness, to society, to the idea of nations and the idea of war. Like these higher level principles exist on our plane of existence, um, and are irrelevant to what happens at the lower levels. And in fact, some of the aspects of the lower levels are irrelevant to what happens at the higher levels, as demonstrated in these cases. This is these examples that he's going over are very clear demonstrations of this fact. Got a comment. Sorry, didn't mean to send you off on another tangent. No worries, that's fine. I'm pretty good at like recollecting myself after going off on a tangent. But I recently discovered it and found it pretty profound. Yeah, thanks for letting me know about it. It might end up being, um, might end up being more relevant to this discussion than I realized or than I predicted. And I might even end up using it in my videos about free will. If that's the case. I've noticed that like things that are relevant to what I'm doing just happen to come to me, and this might be an example of it. Like you just happened to join this stream and then give me what I needed to like solve a piece of this puzzle. Um, because like I mean one time there was like I was kind of distracted while doing some research for this, and I was reading a book, like a novel called Blood Meridian, very famous. So there's a good chance that you heard of it. While I was doing research, I'm a very like sometimes my ADHD is just very out of control, and so like it's useful to have like two things where like one thing I distract myself with, and then the other is like the thing I return my attention to. And so I was distracting myself with this novel, and like at a point in the novel, I realized that what the novel was saying was completely relevant to what I was studying, and I was studying the same thing, this emergence theory. And that was kind of a weird coincidence that I would read a passage from this novel that seemed completely applicable to like my research into free will. Um, that just set me off on another tangent. But yeah, so yeah, no worries about it. So you need the right concepts at hand. The reason is that spontaneous symmetry breaking takes place, so the symmetries of the equation are not shared by the solution. Okay, I need to meditate upon this a little bit. Maybe I'll take a bite as I um, think about it, and you guys think about it as well. They're not shared by the solution? The symmetries of the equation. I need to know more about symmetries and like concrete examples. I've I've been introduced to this concept for a while, but I have never fully grasped it. And I knew that it was something like very profound. Like I knew right away that like this is like some deep shit about reality. But yeah, thus far I have not fully understood it. Um, okay, let's continue. So yeah, spontaneous symmetry breaking occurs so that the symmetries of the equations are not shared by the solution. Oh, okay, yeah, no. If I just wrap my head around that, I feel like I'll have a very powerful tool um, for showing how strong emergence can exist. I like my approach though, which is based on undecidability and computational incompleteness.
This leads to the properties P of emergent highly ordered structures, such as crystals that, through their ordered nature, lead to everyday properties such as stiffness and optical and electrical properties, but also can lead to complex behaviors such as superconductivity and superfluidity. So, those properties, so like back up here, he mentioned the emergence of properties and the emergence of systems. Um, and systems, pretty easy to understand how they emerge. But then properties, it appears that properties um, emerge out of these highly ordered structures, emergent structures, um, which cause some kind of symmetry breaking. Um, and then lead to new properties such as stiffness, optical properties, electrical properties, superconductivity, and superfluidity. So these properties are seem to come about not just from the arrangement of this higher level system, but because this higher level system imposes a kind of symmetry breaking on the microphysics. And it's that relationship of breaking the equations of the microphysics, which gives new properties, which allows for new properties, which is super next level and super profound. Um, whoa, like whoa, like it's. I guess the profundity of that particularly comes from how complex it is. It's not just that like molecules are giving like or atoms are giving rise to molecules, and then molecules give rise to higher things. Those higher things, those molecules, are now having this downward causal influence on the atoms. Um, and so this relationship is kind of circular. Like the atoms cause the molecules, but then the molecules also cause some changes in the atoms. And these changes facilitate brand new properties. Um, so yeah, multiple like things there that are quite interesting. And I've got to like figure out what is the most relevant to my discussion of free will when I attempt to write my video tomorrow. Um, but let us proceed. In crystals, this depends on phonons. Um, yeah, that'll probably become more clear as we discuss this. There exists a wave macro particle micro duality in crystal structures, which provides the crucial interlevel link in emergence properties. So something at the micro level and something at the macro level interact with each other to give these emergent properties. And again, those emergent properties are taken to be strongly emergent. So you can't actually prove that you can't actually predict them from the lower level laws. And I think that's like key here. And another thing that I keep like reiterating is that just because something exhibits strong emergence doesn't mean that it has free will. What I'm claiming is that free will is itself a strongly emergent property. And it has all the characteristics of a strongly emergent property, but that doesn't mean that every strongly emergent property is free will. A strongly emergent property can be something like electrical conductivity, or evolution, or agency. These are emergent properties. Language, that's another example. These are emergent phenomena. And what I'm saying is that free will is an emergent phenomenon itself. It's this brand new thing. It's not a metaphysical property of the universe. It's this new thing that has come about as a consequence of evolution. And that's something that I really need to reiterate. Downward emergence is here because the crystal structure is responsible for the existence of phonons at the micro level. So this is so this is like really explaining how this actually works, how this downward causation occurs. It's because the crystal structure creates these kind of quasi-particles, okay? And it's not quasi in the sense that these particles don't exist. It's quasi in the sense that these particles are a consequence of the crystal structure itself. But these particles operate at the micro level. So this macro phenomenon is giving rise to this micro level phenomenon, which then interacts with the other elements of the micro level. So the electrons of the crystal are now being influenced by these phonons, and the phonons themselves are a consequent or an emergent phenomenon from the crystal structure. These lead to the emergent properties that occur at the macro level in semiconductors. Thus, downward effects shape the lower level electron dynamics due to the higher level crystal structure. These effects are not being directly implied by the lower level interactions by themselves. The key here is that the fact that the higher level phenomenon gives rise to phonons is what's allowing the higher level phenomenon to interact with the lower level phenomenon. So the mechanism for downward emergence or downward causation is very literal. Like, there's nothing magical about it. It's not just like the crystal structure somehow influences the particles. Like, no, it influences the particles because it creates these things called phonons, which then interact with the lower level physics. So it's very literal and very direct. And again, you can't show the existence of phonons from the lower level physics. You got to get to those higher levels first. And then you see how phonons arise, and then you can apply them to your model to get the right answer. So downward emergence, the higher level context alters the lower level dynamics by introducing into it quasi-particles, such as phonons, that play a crucial role in solid-state physics. So it explains how the higher level dynamics give rise to these quasi-particles. And the phonons are real. They're not just a descriptive tool. That's important because oftentimes in physics you'll see reference to like virtual particles. And it's clear that virtual particles are more just like an abstract tool that we use to calculate, like, for example, the vacuum energy of a field. We make this assumption about these things called virtual particles. And that allows us to do field calculations. But it's not like that here. The phonons are real. The phonons do exist as a consequence of the crystal structure. They are real phenomena. They're actually, a good way to understand them would be to think of like, if you have a semiconductor, or like even if you just have like a normal conductor, just like something conducting, some material conducting, you can model the movement of charge in terms of electrons moving towards the positive pole of a battery, or you can think of positive charge moving in the other direction. And there's a sense in which there is actually positive charge moving in the other direction. Even though we think of the electrons as being the parts that move, there is the movement of positive charge in the other direction. I mean, it's a good question whether that's a conceptual tool or whether that's actual. If anybody who's familiar with electricity or electronics wants to weigh in on that discussion, I'd like to hear your thoughts. But let's move on. The Cooper pairs responsible for superconductivity. I'm not sure what Cooper pairs are. I might need to go back to the paper to get some clarification on that. Responsible for superconductivity are similarly downwardly emergent. Okay, you see, I don't even need to know what these are. I just know that there is some kind of new principle emergent in the phenomenon of superconductivity. The Cooper pairs responsible for superconductivity are similarly downwardly emergent lower level effective variables, which can be regarded as produced either by electron-phonon interactions at the lower level or by crystal distortions at the higher level. They would not exist were it not for specific kinds of crystal structure. So superconductivity is itself a strongly emergent phenomenon. And based on the way that he's modeled strongly emergent phenomenon, that seems to be the case, that it has to be strongly emergent. Microphysics M cannot be causally complete. Boom. So that's I think I asked ChatGPT and it says that this is related to mathematical incompleteness, but I think it's just fundamentally the same thing, just being described for an actual mathematical description. So I hope that's enough reason for me to use incompleteness as my kind of ticket to understanding these emergent phenomenon, because I think it's the best way to understand it. I mean, I've understood incompleteness for a while. I didn't fully understand the implications of it. I just knew that it was some next level deep thing that occurred within mathematics that was very puzzling. But now I'm starting to see that if
real life mathematical equations. So, like, for example, the equations of physics. If these equations exist and really describe our reality, it must follow that there are truths expressed within that system of equations which cannot be derived from the equations themselves. Um, and this can be rather complicated because either these truths just somehow exist in the system, or you can add them to the system to change its behavior. I'm not sure which of these is the case. I definitely got to think about that a little bit more to see which is more likely. But yeah, that's very cool. It's very cool that the universe is like this. Okay, an example of microphysics is the following. In quantum chemistry, one first specifies the fundamental physical interactions, electromagnetic, strong and weak nuclear, etc., then enumerates the relevant particles and their properties. So you have things like nucleons, electrons, properties like charge, mass, etc. Next, one lists the pairwise interactions among the particles. So like electrons are attracted to positive charges because they're negative, yada yada yada. Finally, one writes down the kinetic and potential energy operators and adds them to the system Hamiltonian, an expression for the total energy of the system. With the Hamiltonian in hand, one then proceeds to derive the properties and behaviors of the chemical system in question. So this pretty much just summarizes what the materialist position is supposed to be, the reductionist position, that like somehow you can use these very fundamental laws of microphysics to get everything. To get, for example, the laws of evolution or the laws of society, of psychology, of like higher level principles, of music even. Like the principles of music can somehow follow from these microphysical principles. But to quote Dave Chappelle, it's just not that simple, and the universe just doesn't work like that. And there's reason to even think that if the universe did work like that, the universe would be way simpler. Like the crazy complicated structures that compose life, that compose your body, you specifically, your body, for you four of my viewers, like that structure would be impossible if strong emergence wasn't a thing. Like our universe should be way simpler if you could just derive everything from fundamental rules. But because fundamental rules are causally incomplete, it allows for the existence of brand new, unexpected phenomena in this universe. And my God, that's a crazy realization. That's why I'm saying all of this is really enlightening, and why I'm so interested in it all of a sudden. Okay, let us continue. Claims that gravity is symmetry breaking. Claims that gravity is a symmetry breaking contextual term from downward causation of the Earth. So gravity is emergent and needs to be added in some cases of quantum mechanics, like cesium fountain clocks. Yeah, I think this was just like a note in his paper. And I was like writing my own note or my own summary. I do wonder, because I need to talk to a physicist about this. Whether you can think of gravity as an emergent phenomenon, which actually breaks quantum mechanics, because it does. Like general relativity does not work with quantum mechanics. They're paradoxical, and yet we know that both are true. But the question is, why don't they work with each other? And what does it mean that they don't work with each other? Is it a similar case of like this higher level principle changing the rules or breaking the rules of the lower level principle? We have to consider that. We definitely have to consider that. And that's what I like about this paper, is that it's bringing up a lot of questions and making me reinterpret a lot of phenomena that I used to know. Like, I just used to consider the conflict between quantum mechanics and general relativity to just be like a puzzle that's going to be solved eventually. I even thought about like possible solutions to it. But now I'm starting to realize like maybe there is no solution. Maybe they're just not compatible because they're not compatible. The same way like the laws of economics are not compatible with the laws of physics. Like they're just they're different domains. We shouldn't expect them to be compatible. Um, but that makes me wonder like are the higher level laws like universally consistent? Like what if they're not? Like that's trippy to think about. It's trippy to think like in a different star system, like gravity might function fundamentally differently because there's no reason for it to function in a consistent way throughout the entire universe. Um, that's a good question. Oh man, that's making me ponder a lot. Okay, let's continue. Um, Here, the needed spontaneous symmetry breaking takes place at the microscale. I should have taken better notes. Okay, so he's saying that it's the symmetry breaking at the microscale as opposed to the symmetry breaking at the macro scale. I should have wrote that down because I remember that that's mentioned in the paper that spontaneous symmetry breaking actually it comes up again down here, so um, maybe it'll come up. Um, okay, here the needed spontaneous symmetry breaking takes place at the micro scale. For example, via the Higgs mechanism resulting from the Mexican hat shape of the Higgs potential. I'm familiar with this. It's quite interesting, actually. What's going on here? The Higgs mechanism itself has a kind of broken symmetry in it. Um, okay, then macro symmetry breaking is in principle deducible in a bottom up way through coarse graining this symmetry um, broken microstate. Weak emergence takes place. Okay, so I might have been mistaken when I spoke earlier. Then macrosymmetry breaking is in principle deducible. So some kind of symmetry breaking at a micro scale occurs, which then can also cause symmetry breaking at the macro scale. Um, Through a bottom up way, through coarse graining. What does coarse graining mean? Coarse graining this symmetry broken microstate, and this is an example of weak emergence. Um, okay, so I need to know what coarse graining is. We'll just highlight that in case I forget to look into it. Um, so the breaking the Higgs symmetry is weak emergence. Okay, that's useful. That's useful to know that the emergent phenomenon from the Higgs mechanism. So the Higgs mechanism is basically just what gives everything mass, and there's a broken symmetry with respect to the Higgs mechanism, which is what I think. Hold on, there's a bunch of things in my head. I need to maybe look into this again. But basically, when the Big Bang happened, there was this period of inflation. And the inflation is very hard to explain unless you posit something like a broken symmetry occurring within the Higgs field. And so broken symmetries are very crucial for like life and the universe to exist in the first place. But he's saying here, I think he's saying, is that this breaking of the Higgs symmetry is an example of weak emergence. And it'd be very useful to have a few examples of weak emergence on hand. So I'll hopefully remember that. And then he shows this equation, which has to do with the breaking of the symmetries of M. I need to go back to the paper to like make sense of these symbols. But I remember as I was reading the paper, the symbols made sense. I mean, some aspects of it. I still don't know what coarse graining is. So C is a coarse graining operation which commutes. It's supposed to be which commutes with symmetry S. Okay. Let's just jump to the conclusion. Conclusion: Spontaneous symmetry breaking cases at the micro level can produce the required symmetry breaking at higher levels M through weak emergence. Okay, so lower level phenomenon has some kind of symmetry breaking, and it can be responsible for weak emergence. That's interesting, because normally I would just think of weakly emergent phenomenon as just happening, not involving a symmetry breaking. But he appears to be showing that symmetry breaking at the micro level can cause weakly emergent phenomenon. I mean, I guess I kind of knew that already. I just never thought of them as being weakly emergent. Okay. However, while of fundamental importance in the standard model of particle physics, this is not relevant to situations such as the emergence of properties of semiconductors and metals. I love it. I love this author. Here, the needed symmetry breaking does not take place at the microscale, but rather through emergence of the macro scale due to the due to interactions that minimize energy of the emergent structure. Think of atoms crystallizing to form a crystal, for instance. Let me get back to that. But rather through emergence of the macro scale. So the macro scale emerges, and then due to interactions that minimize energy of the emergent structure. Okay, so like some kind of like attempt by the structure to minimize its energy is responsible for this. Think of atoms crystallizing to form a crystal, for instance. This is spontaneous emergence of the breaking of symmetry S at the macro scale M. Hence, is a case of spontaneous symmetry breaking at the macro scale. Let's read that again. The spontaneous emergence of the breaking of symmetry S at the macro scale M. Hence, is a case of spontaneous symmetry breaking at the macro level. In notional terms, if is the process of emergence. Okay, I don't know what I wrote there. And then we have this notation. Thus, the emergent broken symmetry at the macro scale reaches down to affect conditions at the micro scale. This is okay, so first of all, it's crazy that this is true even for like an inert object like a semiconductor. I mean, I guess it's not really, it's inert, but like it can do very uninert things, let's say, but it is fundamentally inert. It's crazy that this can happen at an inert scale, but what I'm claiming is that free will can do this at a much higher scale. So like I can reach down and affect the macro world because of my consciousness of the macro world. So like, for example, nuclear bombs don't just happen spontaneously according to the laws of physics. An intelligent being can understand the laws of physics. Oh man, I just wish like, why don't people realize that like the fact that we're entities that can understand the laws of physics is sufficient to show that there's free will? Because what is an entity that can understand the physics of the world? Like what is that? That's a new thing. Like there has to be a difference between simply experiencing the laws of physics playing out and actually being conscious of the laws of physics. And what I'm claiming is that a being who's conscious of the laws of physics can manipulate physics and cause things that don't normally happen in physics to happen. For example, uranium enriching itself at sufficient concentrations to produce a nuclear bomb. That doesn't just happen in nature. It happens because an intelligent being caused it to happen. And so that's what I mean when I say that free will is this emergent property which rises up out of the physical world and they can have this downward influence on the physical world and alter the trajectory of the physical world because it itself kind of obeys rules and exists at a level which is transcendent relative to those physical laws. And you can prove that this is the case, and you can prove that simple things like semiconductors, as is being discussed in this paper, are examples of that exact same phenomenon, but just taking place at a smaller scale. So again, thus the emergent broken symmetry at the macro scale reaches down to affect conditions at the micro scale, thereby causing effective symmetry breaking at that scale. This produces from M microtheory, an effective microtheory M naught. So okay, so I should have specified that this little m just refers to a microtheory. So like think of like your basic laws of physics for particles, and this m, this higher m, is like a theory that applies to like for example like molecules, or like any higher level concepts would be your macro theory. So you have your micro theory and your macro theory. And when there's spontaneous symmetry breaking at the macro scale, it can cause this downward effect on the micro scale, and it changes the theory. So your theory M now has to become this other theory. So like the laws that we're supposed to apply are supposed to be relevant for your micro theory. In this particular context, because of the emergent phenomenon, this new theory has to substitute, which he's calling M naught. So like if like you have your laws of physics, you might need to like rewrite those laws of physics in particular cases. Maybe not drastically, but just a little bit here and there to accommodate what's going on. An effective microtheory M naught that breaks the symmetry S. Let's see, is that expressed here? That's expressed here. So the symmetry of this of equation is broken. For example, by including phonons or other quasi-particles in the dynamics that can therefore produce the required symmetry broken macro theory by coarse graining. Still don't know what coarse graining is. I wonder if it's a concept that I already know intuitively or if it's something that I need to learn. Okay. At the micro level, a micro level variable is added, AM, that is determined at the macro level conditions and breaks the symmetry S. So this is the addition of a new variable at the micro level, which you need to incorporate in this particular system in order to get the mathematics to work within this context. And again, different contexts will have different rules and different kind of variables that you need to add. And you can even think about like brand new phenomenon occurring because you just substitute this variable with different variables, and so you get a whole class of different phenomenon occurring. And that really explains why there's a huge range of phenomena that happen at smaller scales, because you would think that the micro world of particles would be fairly simple, but actually there's like a whole class of different phenomena that occur at these scales. And so it could be a case of simply like what's being described in this paper occurring, as in for every kind of different phenomenon, you need to add a new variable at the micro level to accommodate that phenomenon. And again, different variables will give you different effective theories. It would have been nice for me to provide more context for these equations if you guys wanted to understand them. How are you guys, by the way, my 4 viewers? You can say something or not, up to you. Okay, let's proceed. Where are we at now? Okay. This is the way that effective theories for physics involving symmetry breaking can be derived. You apply a coarse graining process C to M naught, not M, and thereby obtain the macro theory M that breaks the relevant symmetry and accords with experiment. That is, and then he explains it in notational terms here. Okay, let's think about that. Okay, so I'm guessing based on the context here that coarse graining refers to just derivation, so like deriving your higher macro theory, and that you can only do that for the modified theory. So you have your micro theory, but then it has to be like a modified version of it, and then once you coarse grain it, so derive it, you can obtain the macro theory that breaks the symmetry so a symmetry has to be broken in order for this M naught to occur. So this is a different theory that's like, it's similar to M. It's similar to M theory. Not M theory, but the theory that we're calling M. But it probably just differs in a few ways. And then when you take this theory, you can eventually derive your macro theory. But the only way to get this micro theory, this M naught, is after the principles of your macro theory have had their effect on the micro scale, possibly by introducing this variable AM that's described here. Okay, that makes sense to me. Hopefully it made sense to you as well. Continuing on. So this is what they do in quantum chemistry. By adding the fact that nuclei are far heavier than electrons. Again, I don't know whether, it's a good question, whether you can use the laws of the standard model Lagrangian to calculate the mass of a nucleus. And if you can, that would be an example of weak emergence. There's nothing like complicated going on there, but this seems to be applying that you need to add this in a after the fact manner in order to do quantum chemistry, by adding the nuclei that are far heavier than electrons to derive a new microtheory M naught. Okay, so you use this fact. So you have to add in this variable, the fact that nuclei are heavier than electrons, and then this will give you a new theory, M naught. So
this M naught theory does not apply to nuclei and electrons as they're normally described. It only applies when you add in an additional factor, which is that the nucleus is far heavier than an electron, which I guess is which is in and of itself not implied by the fundamental theory. So it's a new theory. It has to be a new theory. It's a slightly different M. Okay, this is making sense. And this apparently breaks the translational symmetry and gives the required results. I don't know where's the translational symmetry though? Where does translational symmetry feature into quantum mechanics or into particle physics? I would need to know where that actually fits in. Excuse me for a second while I take another bite. Okay. Gives the required results. It is not the same theory that you started with. It is the lower level effective theory you need. That's interesting though, because you can get these slightly modified lower theories, and then they're supposed to be able to give you the higher level principles. So there's a sense in which you can get to higher level principles from these lower level principles as long as they're the right principles. But maybe, hold on, so maybe that does have to relate to incompleteness, because it's like an additional factor that you need to add to that theory in order to get it to work at higher levels. Yeah, no, I can buy that. That makes sense. Okay. If we don't use a new effective theory at the lower level, the correct emergent results cannot even in principle be deduced in a purely bottom-up way. So if you have the wrong theory, if you don't have those new principles, you just like it's funny how it says not even in principle. It implies that like there's this it's not just like a matter of like practicality that prevents you from getting the higher level principles. There's like something in the rules of mathematics itself which prevents you from deriving higher principles, which is rather fascinating. This contradicts the known macro level symmetry. symmetry breaking of M. You can't get uppercase M from lowercase m via any coarse graining C that does not break the symmetry S. Okay. I think I understand what coarse graining is now. It just could be like a way to talk about derivation. Mathematical derivation using mathematical rules. If anybody has anything to say, by the way, please feel free to either ask questions or give feedback or express yourself in any way. But yeah, no, I'm very glad that I went through these notes again because I'm getting a lot of insights. There's still so much. Jesus Christ. Jesus. How am I supposed to do this? But at least, like, I hope that, like, just discussing it out loud with people who I hope are listening will, like, put a lot of this information in my brain so that when I go and write the script for my new video, I will be able to do so more seamlessly and, like, know where to start. Okay, conclusion. Strong emergence of properties P takes place when spontaneous symmetry breaking M occurs. Okay, let me go back because this is important. Conclusion. Strong emergence of properties P, of brand new properties, takes place when spontaneous symmetry breaking of the macro level, at the macro level, occurs. The symmetry broken higher level dynamics cannot even in principle be obtained by coarse graining the fundamental theory M because the symmetry of M isn't broken. One has to coarse grain the effective microtheory M naught of such a nature that the symmetry is broken to get the correct result by M coarse graining. So a symmetry has to be broken. That's very interesting. If at the micro level a symmetry is broken, you can use that symmetry broken level of the equation to get to coarse grain to your higher level theory. A couple things. Like, I'm not sure what the source of the symmetry breaking is because it says it has to occur at the macro level, and it said up here that if it occurs at the micro level, like, there's nothing that's just weak emergence. So I guess it happens. Hold on, let's see the notation. Maybe the notation will make it clear. Okay, so yeah, so the symmetry breaking occurs at the macro level, and then it's what causes somehow this. Okay, so this produces an effective theory M. Reaches down to affect conditions at the micro scale, thereby causing effective symmetry breaking at that scale. Okay, so it causes effective symmetry breaking. It's not like literal symmetry breaking. It's just effective. At least I think it is. And that's what causes there to be this new theory M that you have to consider when you want to do your higher level dynamics, or when you want to derive your higher level dynamics. Okay, so one has to coarse grain the effective theory M naught of such a nature that the symmetry of M naught is broken. So, like, okay, so it's like double. It has like this, it feels like there's two symmetry breakings going on. There's a symmetry breaking at a higher level, which causes a symmetry breaking at a lower level, which is how you get this new M theory, which will get you the correct result when you coarse grain it. I mean, it's still, like, the thing that's kind of like throwing me off is the fact that you can still coarse grain your way to the higher theory. It just has to be the correct theory at the lower level. But that feels like it conflicts with the idea that I've been repeating over and over again, that it's impossible in principle to use those lower level principles to get the higher level principle. But it's not that simple. Like, it just feels like that's the case because I'm dumb and I don't fully understand it, and it's kind of like contrary to my to the way I already understand things. But it's consistent. Like, it makes sense. Like, it's because it's this double interaction of You have this macro level. The macro level breaks the symmetry. The symmetry breaking causes this symmetry breaking at the lower level. The symmetry breaking at the lower level means that your effective theory that you started out with is wrong, so you need to replace it. And then with this replaced theory, you can now work your way up to the higher theory. And that makes me wonder, like, is it true then that you can coarse grain some kind of version of quantum mechanics and then get free will as a result? But then there's other issues to consider, because the fact that free will is having a downward causal influence on matter. Okay, lots to think about. But I hope that this is still relevant to free will. I think I wrote a note here. I think this means you need to break the symmetry of a microtheory to get the correct result M by coarse graining. Yeah, I do think that. In short, you have to add a symmetry breaking term into the microtheory in order to get the correct macro theory, because it's not there in the fundamental physics. But you can only work out what symmetry breaking term to add from your knowledge of the correct macro theory M. You have to use variables defined by that higher level theory to get the symmetry broken effective microtheory, which gives you the correct macro result M. Yeah, this is... Okay, let's just highlight this. That's cool. And I think that makes sense. But it shows that, well, it shows a lot of things, actually. it shows that, like, if we just guess about a kind of theory, or about I guess about a kind of law that we can add to our microphysics, we might be able to come up with novel phenomenon as a result of that law, and then maybe even check whether that that novel phenomenon exists in the real world. And if it doesn't exist, check whether we can create it. That's interesting. That's very interesting. And I wonder whether that's now possible given what we know about the nature of emergence. Okay, so, man, I haven't gone through this paper. Ugh. Okay. Somehow, for some reason, talking about phase transitions now. Water is an all or nothing phase transition. The symmetry alteration at a temperature is needed so that new rules apply. And temperature is a macro scale property that is exerting influence. Okay, so this is definitely my note, because you can tell that it's my note because of how badly written it is. But I think, okay, so this is a very key insight here, because it must have come up in the paper. So water is an example of, like, symmetry alteration, because you have water at, let's say, like, room temperature, and you know how it works, but then you increase the temperature, and now suddenly it's becoming a gas. And those rules that you can apply to understand its dynamics as a liquid don't apply to its dynamics as a gas. So symmetry has been broken because of temperature. And temperature itself is a macro phenomenon. It's not a micro phenomenon. You can't measure the temperature of an individual particle. When you measure temperature, you're measuring the average movement of a bunch of particles. So you need, by definition, a bunch of particles in order for it to have a temperature. But temperature itself can induce symmetry breaking in water. And then I guess at each kind of phase transition, so for example, for boiling water, there's this different set of rules that applies. So you need a different micro theory. And then for frozen water, ice, you need a different set of rules that apply at that level. Okay, so this is a good example for understanding this concept. And I wonder, like, is it going to be a waste of time to explain all of this from the perspective of physics and, like, microphysics if, like, I'm trying to explain free will? Because somebody will, like, interrupt me halfway and still be like, well, you still don't have control. You still don't have control over the fundamental particles. And I'll be like, well, no, I'm just making a point from the fundamental particles, and what I'm going to show is that this generalizes to free will.
Oh man, I'm anticipating all sorts of like counter arguments and arguments, and then like developing my arguments for their arguments. Um, but the fact that I believe in free will gives me an advantage because I can use my free will to simulate what I think is going to happen and then pick the appropriate course of action. Just like Paul Atreides, if you're still there, Mateo. Okay, let's continue. We'll maybe go for like 10 more minutes. Consequent on this symmetry change, the properties P of the substance change from being weakly emergent to strongly emergent. Consequent on this symmetry change, the properties of P of the substance change from being weakly emergent to strongly emergent. Man, it's just so cool that strong emergence even exists. This is similar to what happens when molecules form out of atoms. A key comment is the following. When this takes place, the relevant Hilbert space of the problem changes completely. What the hell is a Hilbert space? Let's highlight that. Maybe highlight a different color. My dog wants to come inside. So let me grab him. Any questions or anything so far? Or anything anybody wants to say? You can take this opportunity to say something irrelevant. Like if you want to talk about something else, feel free. Like if you want me to talk about Jung or another topic, feel free to ask about it. Like just take this as your opportunity to interact with me. Even though I'm doing one thing, like I can multitask. I have ADHD, so I can multitask. Which is what my therapist told me. But I need to know what a Hilbert space is, so if anybody knows what that is. This is how properties P become strongly emergent when a crystal or molecular structure arises through weak emergence, E, via strong spontaneous symmetry breaking at the macro level. Emphasizes that spontaneous symmetry breaking leads to singular points and thus a breakdown in continuity. Yeah. I understand that kind of. Matt G said it's basically a vector space, but with potentially infinite dimensions. Okay. Okay, and does that apply for any kind of set of mathematical principles? Because it's saying here that basically, I think it's when strong emergence occurs, the relevant Hilbert space of the problem changes completely. So it's like vector space, but with potentially infinite dimensions. Is it the space that the vector exists in, or like the potential possible spaces that the vector can occupy? I mean, I can see how that like a general form of this is relevant to mathematics and strong emergence. It's just like the space of possible answers just alters completely when strong emergence occurs, because we're just fundamentally dealing with a different problem. Teddy, come here. Come here. Yeah, come here. You want this? Okay, here, go. Sit. Down. Teddy down. Teddy sit. Teddy down. Teddy floop. 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 Good boy. Okay. But yeah, I'd like to hear more if you have more information. I'll Google it and like look into it. Okay. The laws of physics are effective laws. Despite the fact that they are effective, eternal, and unchanging. All the well-established and tested laws on which physics and engineering are based are effective laws. So an effective law is like is a law that's applicable to a particular domain, either because of strong emergence,
because strong emergence means that it is only applicable to that domain. Um, so of the form 8. This applies equally well to Newton's laws of motion, Newton's law of gravitation, Maxwell's equations, Einstein's gravitational field equations, the Schrödinger equation, Dirac's equation, and the standard model of particle physics. They all only hold in a restricted domain. That's cool. He's claiming that all these like fundamental laws of physics really only work in a particular domain. And that's exactly what an effective theory is. Like because of strong emergence, whatever theory you had will no longer be applicable to like this higher level domain. And so this higher level domain requires like new laws. And so whatever laws you derive and are applicable at that domain are only applicable at that domain, and not applicable at higher levels, or at different levels, either lower levels or higher levels. And so all of these laws of physics are actually such theories. And every theory has a domain of applicability. So again, how this relates to free will is that you might argue that all human behavior and everything that we do is, at its most fundamental level, just the laws of physics, just the laws of particles, just particles hitting particles, and particles interact in very specific, predictable ways, and that's all a human is. Or at least you would think so, but it's actually not true, because those laws of physics really only apply to like individual particles. Like it's even questionable whether they apply to like bigger arrangement of particles. And so their domain of applicability is only applicable to like very small particles. But once those particles arrange themselves in sophisticated structures, new laws take over, and so those old laws need to be replaced or modified. This can happen very dynamically, such that something like consciousness comes into existence, and it has this dynamic influence on those lower laws, such that you really can't ever get to consciousness from the lower laws. It's just not possible in principle, and because the principle behind it is because consciousness is having this this downward influence on the laws of physics and altering them in that sense. So downward causation occurs through microtheory M, giving rise to microtheory M naught, with a variable A. And A here is a variable that cannot even in principle be represented in terms of the micro level variables occurring in M. So it's this brand new variable that you derive or that you discover, let's say, at the macro level, and then you can throw it into your old theory, modifying it, and then this will give you the correct answers. But there's no way to get to this variable from the microphysics. Like the microphysics is incomplete. There's an incomplete truth within the microphysics that cannot be shown to be resultant or consequent from the principles of the microphysics. It's some brand new truth that exists within that system. And once you know what that truth is, you can add it in an after the fact manner to get the correct results, if that makes sense. Okay, let's read one more line and then I'll just cut it here. All the variables occurring in microphysics M respect the symmetry S, whereas the variable A that occurs that's derived from the macro level, and so M naught does not. So yeah, the symmetry S. Let's see if there's symmetry S. The symmetry S is broken in this situation. So it's all about symmetry breaking. Like the symmetry breaking is the key here. And I'm glad that it does have like a very solid foundational basis. Okay, so it's past 10 o'clock right now, so I should definitely start winding down. Oh, basketball game is going on. Oh, clicked on a wrong tab. Okay, yeah, so thanks for watching, my 4 viewers. You feel free to say something now if you want, to acknowledge your existence. But yeah, thanks for watching. Take care, have a good night or day wherever you are, and I'll see you on the next one. And hope you continue to watch my videos and tune in for future streams. Yep. See ya.